Hello my dear students. So in my last class, I started explaining about third law of thermodynamics. So there we saw what does the statement of third law of thermodynamics says about. So as I have mentioned in all my thermodynamic classes, so the first thermodynamics, that is the first law of thermodynamics, it introduces a new term, what is called as enthalpy. And the second law of thermodynamics, it introduces a new term called as entropy. And in the third law of thermodynamics, so we are going to study about free energy. So there are two different types of free energies what we are going to see. So in that, one is Helmholtz free energy and another one is Gibbs free energy, right? So in third law of thermodynamics, according to the discussions what we have done in our previous classes, so we saw about the statement what is the third law of thermodynamics, that is at absolute zero temperature the entropy of a perfectly crystalline substance is zero. So this is what the statement of third law of thermodynamics says about. That means here entropy means what? Entropy is a measure of randomness or disorder of the molecules. Okay, so make it very simple. If I explain the third law of thermodynamics in simple terms, so how we are going to understand it is, so the third law states that the entropy of a perfect crystal of a pure substance approaches zero as the temperature approaches zero. That means when the temperature of the system or the process which is going on, so when it attains zero temperature, so when the system attains the zero temperature state, at that time the entropy of a perfect crystal of a pure substance also approaches zero. At this time, the alignment of a perfect crystal leaves no ambiguity as to the location and orientation of each part of the crystal. Okay, so this is what the third law of thermodynamics explains about, and this is the simple term, the simple way of understanding the third law of thermodynamics. The third law of thermodynamics has two important consequences. We have to observe two important consequences. What are those? So that is the first one, it defines the sign of the entropy of any substance at temperatures above absolute zero as positive. Okay, so this is the first consequence. That means so the entropy of any substance at a temperature which is above absolute zero will be always positive. This is what we are going to understand from this, and it provides a fixed reference point that allows us to measure the absolute entropy of any substance at any temperature. Okay, so this is what the third law of thermodynamics explains on the basis of two important consequences. Okay, so this is a brief introduction of third law of thermodynamics, and next what we saw or discussed in third law of thermodynamics was applications of third law of thermodynamics, where and all we are going to use this third law of thermodynamics. And next we went through free energy. What is meant by free energy? That is free energy is the maximum amount of energy available to a system during a process that can be converted into useful work. So this is how we are going to define free energy, and we derived also a mathematical term which defines the free energy, and further we also deduced two equations where one is Helmholtz free energy which is symbolized by capital letter A. Okay, and next is capital letter G, which was known as Gibbs free energy. And also further we saw the relationship between Gibbs free energy and Helmholtz free energy. And next what we discussed was spontaneity of a reaction, right? So how the reaction processes, whether a given process takes place spontaneously or not, depends on two factors, that is one is change in enthalpy and change in entropy. So this was understood in our later on concepts, and then we jumped into the mathematical derivations of variation of Helmholtz free energy, that is what is called as work function with temperature and volume. And next, so variation of Helmholtz free energy with the temperature during an isochoric process and also during an isothermal process. Okay, so all these concepts were discussed in our previous class. So hardly our previous class was 1 month back. Okay, so due to some reasons, so I was on OOD, so I just blow up the syllabus, what and all we have discussed in the topic third law of thermodynamics, that too especially in our previous class. And also I told you while ending up my previous session class that we are at the end of this topic, that is third law of thermodynamics, and also at the end of unit 1, that is the main title under thermodynamics. We are at the end. Okay, so another 10-15 minutes is enough to complete this unit. So for this reason I took some extra 5 minutes to blow up the syllabus what we have discussed in our previous class. Okay, so now moving on to the present class, we are supposed to discuss about variation of Gibbs free energy with temperature and pressure. As I have told in my last class, in the mathematical derivations we saw variations of Helmholtz free energy, whereas in this class we are supposed to understand about variation of Gibbs free energy with temperature and pressure. Okay, so we have G, that is Gibbs free energy, is equals to H minus Ts. Okay, so this is already we have derived in our previous class, where G is equals to Gibbs free energy, right? G is equals to Gibbs free energy and H is the enthalpy, and Ts, so Ts is nothing but unavailable energy. So this is how we are going to define Gibbs free energy. Let me take that equation itself to derive the variation of Gibbs free energy equation here, and let me call that equation as equation number 1. Okay, but according to the definition of enthalpy we know that H is equals to U plus PV. Okay, so this is how we are going to define H. So substitute this value, that is H is equals to U plus PV in equation 1. What I am going to get is equation 1 will become G is equals to U plus PV minus Ts. Let me call this equation as equation number 2. Okay, so this is the first step what we have to do here. On differentiation of equation 2, so this equation we get, so dg is equals to du plus pdv plus vdp minus tds minus sdt. Okay, so this is the differential form of equation number 2. Let me call this equation as equation number 3. From first law of thermodynamics we have du is equals to dq minus pdv. Okay, so this already we have deduced. And from second law of thermodynamics we have dq is equals to tds. Okay, so now here if you observe these two equations which I have taken here, so here there is a term which is called as dq, and according to the second law of thermodynamics we have dq is equals to tds. So I can substitute the value of dq which is equals to tds in this equation, right? See it properly and listen to it very carefully, so that when I substitute this TDS here, then this equation becomes, so from first and second law of thermodynamics we are going to get du is equals to TDS minus PdV. So that is what it has been written here, TDS minus PdV, and let me call this equation as equation number 4. From equations 3 and 4 we get, so okay, so now just combine these two equations. Observe these two equations. So here dg is there, to that du value, so du is equals to tds minus pdv, substitute this value here to equation number 3. Then what I am going to get, dg is equals to, instead of du, see here, instead of du I am writing it as tds minus pdv. Okay, so that I have written it in bracket so that there should not be any confusion. So instead of writing du, so I am writing the value of du, that is tds minus pdv, and rest of the things are same, plus PdV plus VdP minus TdS minus SdT, which is there already in the equation number 3. Okay, so here if you observe it clearly, so what happens here is so this TdS and this TdS, they both will get cancelled because positive and negative. Observe the signs here, so PCM students will understand it in a better way. And next what is going to get cancelled here is PdV and PdV. Okay, so this TdS and PdV, they both will get cancelled, and what is left is dG is equals to this VdP minus SdT is left. Let me call that equation as equation number 5, and this equation 5 is the expression for variation of Gibbs free energy with temperature and pressure. Okay, so this is how we are going to deduce the mathematical expression for variation of Gibbs free energy with temperature and pressure. Okay, next is about variation of Gibbs free energy with the temperature during an isobaric process. Okay, so now you should keep this equation in your mind. Okay, so this is the main equation which we are going to use for variation which we use to understand the variation of Gibbs free energy with the temperature and pressure. Okay, so this equation number 5 is the equation which we are going to use in understanding these two processes, that is variation of Gibbs free energy with the temperature during an isobaric process and during an isothermal process. Okay, so what is meant by an isobaric process? We all know that in isobaric process is a process where we are going to keep pressure as constant. So that means at constant pressure the process is going to occur. So that is why dP is equals to 0. From equation 5 we have dG is equals to minus SdT. Why? Because here see dP is equals to 0, because this is an isobaric process where we have kept pressure as constant. That is why dP is equals to 0. That means this whole term will become 0. Okay, so when dP is equals to 0, this whole term will become 0. So that is why dG is equals to minus SdT. So that is what is left. Okay, dG is equals to minus SdT. Now rearranging this equation, what I am going to get is dG divided by dt, that is under pressure, means at constant pressure, which is equals to minus S. Okay, so if I write it like this, dG divided by dt in bracket, and if I write P in as a subscript, it means that the process is taking place in a constant pressure. Okay, so let me call this equation as equation number 6, and equation 6 describes the variation of Gibbs free energy of a substance with temperature. Okay, so this is the expression. Next, moving on to the next process, that is variation of Gibbs free energy with pressure during an isothermal process. Okay, so as we all know, isothermal process means, so here dt is equals to 0. That means at constant temperature, so the change in temperature dt will be always equal to 0. From equation 5, what is left? Suppose see here, this is equation number 5. So if dt is 0, definitely this whole term will become 0, and what is left? dg is equals to vdp. Only dg is equals to vdp is left. Okay, for an ideal gas, so this is a general representation of an ideal gas. PV is equals to nRT. Okay, so this is we all know. Suppose if I rearrange this equation, let me take V to the left hand side and rearrange this equation, because here there is a term what is called as V. Okay, so I want to substitute the value of V here. So for that purpose I am taking in this equation, that is PV is equals to nRT, I am retaining V to the left side and rearranging by sending P towards the right hand side, so that I will get V is equals to nRT divided by P. Substitute this value V is equals to nRT divided by P here. Okay, here that is dG is equals to nRT into dP divided by P. Let me call this equation as equation number 7. Next is so during a process, let Gibbs free energy change from G1 to G2 when pressure changes from P1 to P2. Okay, so since here, so this is a isothermal process, so here temperature will be kept constant. So that is why, so the only observations what we can make is so there must be a change in free energy, that is from G1 to G2, and that change in free energy will take place when pressure changes from P1 to P2. Okay, so this is the condition of the process. So now integrating equation number 7, integrate this equation number 7 with respect to the limits. So I'm going to get so limit g1 g2 of dg, which is equals to limit p1 p2 nRT into dp divided by p. Okay, so next so this equation can be written in terms of ln, where I can write it as g2 minus g1, which is equals to nRT ln p2 divided by p1. Okay, so this also can be written as delta g, that is because so delta g is nothing but change in Gibbs free energy. So here two Gibbs free energy are there, that means the Gibbs free energy has been changed from g1 to g2. So that is why so this g2 minus g1 can be written as delta g, and rest of the things is same. So delta g is equals to nRT ln p2 divided by p1. Otherwise, so this equation can also be written as in logarithmic form. So if I convert this into the logarithmic form, so then I can write it as delta g is equals to 2.303 nRT log p2 divided by p1. Okay, so this is when pressure is changes from p1 to p2, and let me call this equation as equation number 8. Okay, and similarly at constant temperature we know that p1 is equals to, or p1 v1 is equals to p2 v2, or this can also be written as p2 divided by p1 is equals to v1 divided by v2. Okay, so in the place of p2 divided by p1 we can write v1 divided by v2. Okay, so then this equation takes up the form delta g is equals to 2.303 nRT log v1 divided by v2. Okay, so this is the expression which is derived to explain the variation of Gibbs free energy with pressure during an isothermal process. Okay, so these two are important. Observe these two equations, so that there is two problems which are solved in our textbook. So if we use these two equations to solve the problems, definitely it will become more easier for you. Okay, so what is the problem we will see now. The first problem says that calculate the free energy change accompanying the compression of 1 mole of ethane at 323 Kelvin from 20 atmospheric to 250 atmospheric pressure. Okay, so this is the question, and here he has asked us to calculate the free energy change. Change in free energy means what should come in our mind is delta G. Change in free energy means delta G. So he is asking us to calculate the delta G, change in free energy. And what information he has given? He has given that, so here the compression of 1 mole of ethane gas takes place at 323 Kelvin from 20 atmosphere to 250 atmosphere pressure. That means here he has given temperature and he has also given pressure. Okay, so here we have to use equation number 8. Okay, so take equation number 8, and here P2 is the means the change in pressure. 250 atmospheric pressure is called as P2, 20 atmospheric pressure is called as P1, and 323 Kelvin is the temperature T, and we know what is the value of R, that is 8.314. okay, and he has also given he has also said that 1 mole of ethane, so that is why N is equals to 1. Substitute all the values. So in this, according to this equation, we have N is equals to 1, R is 8.314, and T temperature is 323 Kelvin, and pressure P2 is 250 and P1 is 50. Substitute all these values. We are going to calculate the free energy change accompanying the compression of 1 mole of ethane at 323 Kelvin from 20 atmospheric to 250 atmospheric pressure. Right? In the same way, so here the second problem is calculate the free energy change which occurs when 1 mole of an ideal gas expands reversibly and isothermally at 300 Kelvin from the initial volume of 5 liters to 50 liters. Okay, so if you read this problem carefully, definitely you will get an idea that you have to use equation number 9 here. Okay, so why equation number 9 is he has given initial volume of 5 liters to 50 liters. Okay, so volume is given in this problem and rest of the things is the same. So to solve that problem we are going to use equation number 9. So here n is equals to 1, that is because here 1 mole of an ideal gas is used, so n is equals to 1, and temperature T is equals to 300 Kelvin, and volume V1 is equals to 5 liters and V2 is equals to 50 liters. Okay, so all the informations we have, substitute all these informations here. So what we are going to get, delta G is equals to 2.303 into 1 into 8.314 into 300 log 5 divided by 50. Okay, so 5 divided by 50, substitute that value, we are going to get, or we are going to calculate the free energy change which occurs when 1 mole of an ideal gas expands reversibly and isothermally at 300 Kelvin from the initial volume of 5 liters to 50 liters. Okay, so this completes this unit and also the topic third law of thermodynamics, and in my next class we will start with the reactivity of phenols, right? So the organic chemistry part, reactions and reactivity of phenols, we will start in my next class. Okay, thank you dear students.